All right. So as I said, there are two parts to my talk. In the first part, I'll talk about what I call deep internal learning. That is to say, how we can train a deep network in a totally unsupervised way without ever having seen any prior examples or prior training examples by training on a single image, the test image alone. Why is this interesting? By the way, there's a hush sound here. What is this? No. Okay. Why is this interesting? We're all used to what I call external learning. That is to say we train a network on lots and lots of data provided to us externally. We train the network for days, sometimes even weeks. Then we freeze the network weights and we apply it to new test data as it comes along. And this, of course, does amazingly well as long as we have enough training examples. But what happens if we don't have enough training examples? Or what happens if our test data is outside the distribution of our training examples? In those cases, deep learning fails miserably. And what I'd like to show you today is how we can often resolve these problems by replacing external learning with internal learning. And as you'll see, this gives rise to lots of applications, including spatial super resolution in images, temporal super resolution in video, image dehazing, segmentation, transparency separation, image retargeting, and more. In the second part of my talk, I'd like to talk about a different branch of work in my lab, what we call mind reading. That is to say, how we can decode brain activity and how we can decode visual information from brain activity. A person is in an fMRI machine. We'd like to record the brain activity and then be able to reconstruct back what the person is seeing. And once again, here we don't have enough training examples, and you'll see again how we can resort to self-supervision and handle the lack of training data. In the first part, the main driving force behind the work I'll show you is my former PhD student, Asaf Shocher, who's now a postdoc at Berkeley with Alyosha Efros. And in the second part of my talk, there are three main people behind the work that I'll show, Roman Bailey, Guy Gaziv, and Ganit Cooper-Schmidt. So let's start with the first part. Well, how can we train a network on a single image? It turns out that there's a lot of redundancy inside a single natural image, both within and across different scales of the image. When I say within scale, I mean that if you see a small patch once inside the image, you'll almost surely see it many more times inside the same image. Now here I'm showing you large patches just for visual purposes, but of course I'm talking about much smaller patches, 5 pixels by 5 pixels or 7 by 7. And this property has been used by us and by many others for a wide variety of problems in computer vision, including image completion, image denoising, visual summarization, and whatnot. Less commonly used, but also very strong, is the recurrence of patches across scale in the image. What I mean by that is if you take the image and downscale it, then almost